All right, questions about your homework from last night? No, it was good. Was it good? I felt 24 on the very. I was gonna say, which one are you looking at? Because I don't see a 24. Okay, 14. I have 1/4 to the 2x equals 32 to the 4x minus 2. What base did you switch everything to? Both of these are powers of what? 2. I'd switch it to a base of 2. Because 4 to nothing, you can't raise 4 to anything to get 32. So I'm going to do 2 to the negative 2. Do we all agree with that? The negative flips it, the squared makes it 4. So to the 2x equals 2 to the what is 32? 5. And so I have 4x minus 2. So my equation I'm solving is going to be negative 4x equals 5 times 4x minus 2. So negative 4x equals 20x minus 10. I'm going to subtract the 20x to get negative 24x equals negative 10, and of course divide by negative 24. It's not 5/12. Which one? Give me one. How about 10? We didn't do 10. 4 to the y plus 2 equals 16 to the y minus 3. What base should we make? So we want these bases to be the same because at the end of the day, when the bases are the same, we can just set the exponents equal. So what number can I raise to a power? What number can I raise to a power to get both 4 and 16? 2. 2 to the what is 4? Right? The y plus 2 is still there. You could do 4. Yeah, you could. 16, 2, 4, 8, 16, so 2 to the 4th. You'll still get the same answer, Aaliyah, but you could use the 4 there. So then because the bases are the same, I take this. So I get 2 times y plus 2 equals 4 times y minus 3. So 2y plus 4 equals 4y minus 12. And now I just have a simple equation to solve, yes? I'm going to add 12 and probably subtract 2y. See what happens. 12's are gone, 2y's are gone. Yeah. You want to get the bases the same and then solve for the exponents. 10 on the front. Now again, you didn't have to use, you could have left this a 4 and had 4 to the y plus 2 and changed 16 to 4 squared. You would have y plus, yeah, but it doesn't matter. 2 work here, whatever works is fine. I'm just showing you that if you had not chosen 2, if you had chosen 4, it still works. I could add 6 and subtract y. Still getting the same thing. What else? What else? What else? What else? We can do it. I can show you. So we're looking at 16 on the back. Remember, the goal is that we clean everything up first and then we manipulate those bases to be the same. So here, I can't combine these because the bases aren't the same, but I could rewrite them with the same base. What would the base be? 3, right? 3 to the what here gives you 1/9. What power would I need to put here to make this 1/9? -2. That's exactly right. -2. Good job, Aiden. How about the 1/3? Close. -1. That's exactly right. That's going to flip it. Now these have the same base, so I can add these exponents together. So -2a plus -1a is, that's right, 10. No. You can get it though. What do you think it is? Thanks for your help. We'll set those exponents equal because bases are the same, yes? And now add a to both sides. What's a equal? -8. The more and the better you're able to do the easy stuff. So I think the way I always introduce logs is by telling you why we need them. So why do we need logs? If you get, we've been solving exponential equations, right, where we've got variables in the exponents. And the only way we know to do that now is if the bases are the same, then we just set those exponents equal to each other and solve, right? But what happens if I have something like 2 to the x equals 10? There's no way I can force the same base there, right? Because there's nothing I can raise 2 to get 10. And so so this is where logs come in. Logs are the inverses of exponentials. And inverses, of course, cancel each other out, which lets us solve for things, right? So that's why we need them. We'll get to this later, but I'd just like to tell you why we need them. So what is a logarithm? A log, and this is on your paper, but AKA a log, is an exponent. So you have to remember that logs are exponents, and that'll help you as you start changing forms and whatnot. So a logarithmic form looks like this. You've probably seen this button. Have any of you done logs before? Some of you have, a lot of you, most of us haven't. Okay, so you've probably at least seen the button on your calculator that says log, right? And like, why does my calculator say log? Okay, well, here's why. We write a little teeny b here. That is a subscript there, so make sure it's below, right below the g. It's written right below. So log base b of a equals x. Just so you know how we say this, okay? Log base b of a equals x. And what this means, this is what we call logarithmic form. But because logs are exponents, we can write it in what we call, oh my goodness. It was an ant. It was Fred. We can write in what we call, it's the same ant that stays right here all the time, in exponential form. And so here's how we do that. When we said, we'll try to make this as easy as I can for you because you have to be able to go from one form to the other very, very fluidly. So log base b of a equals x. What do you think the base in my exponential form is going to be? Let me say it again in logarithmic form. Log base b of a equals x. B. Right? Do you see that? B. What? Is an exponent. So the exponent here is going to be whatever the log equals. So b to the x Now this is going to equal, what's the only one left? The only variable left, a. Okay, so this is how we switch forms. Okay, now there is a little trick if you're in log form. As long as the log is written first, log base b of a equals x is the same thing as b to the x equals a, and it makes a little e for exponential. Quirky little silly things that help you remember, right? But b to the x equals a. So let's practice a couple, changing the form, and see what they look like. Number 1, log base 3 of 9 equals 2. Write that in exponential form. What does it look like? Y'all can tell me. We'll do a couple together, and then I'll let you try. 3 to the second power. Easy? Good job, Tanner. Proud of you. All right. How about number 2? Look at y'all go. 6 to the third equals 216. Let's go. This is pretty easy. Right now, this is just changing forms. Okay, wait a minute. Hold up. The next one doesn't make any sense. Log base 7 of 1 equals 0. 7 to the 0. Is that true or false? True. True. Even to the 0 power is 1. How about 4? Log base 2 of 16 equals 4. 2 to the 4th equals 16. Pretty easy so far? It doesn't matter if they're positive, negative fractions, whatever it is, like number 5. It's the same process every time. What does that look like in exponential form? 4. There y'all go. That's exactly right. So some stuff starts coming back that we've already done, right? Anything to a negative exponent flips over. I've got, let's look at this one. Log base 9 of 27 equals 3 over 2. What's the exponential form of that? 9, 3 over 2 equals, you're exactly right. Is that true? How do you know? How do you know, Aiden? 3 over 2 is the square root of 9 to the third power. That's exactly right. The square root of 9 is 3, and 3 cubed is 27. Everybody okay? Let's go backwards then. Let's go from this form to this form. Look at number 7. Told you we were going to start easy and you're going to go, oh my gosh. But you have to be able to understand this to understand the rest. Write that in logarithmic form. Okay. It's log base 14. That's exactly right. Logs always equal exponents. If you remember that, bases are easy to remember, right? And the base is always written little. And logs equal exponents. You only have one thing left to put there. How about, let's get down to number 11. 2 to the negative 3 equals 1 over 8. What's that look like? Log base 2 of 1/8 equals negative 3. Just negative makes it flip, yeah. No, you wouldn't write 1 over 3. No, you're not changing anything on these that say rewrite. You're just writing them a different way. That's all. That's all you're doing. I flip over. We have something that we call common logs. We operate in a base what number system? Y'all know a base 10 number system, right? Every 10 it starts over. We get to 10 and then it's 11, so it's 1 and 1, 1 and 2, 1 and 3. So common logs, you know, math is famous for all these times where if there's nothing written, there's an imaginary blah. Like if it's a square root, there's an imaginary what root? 2 written outside, right? Well, for common logs, if you have a log of whatever, let's just say x, and there's nothing written here, that's an implied 10. Okay, so a base of 10, a log base 10 is our common log. So we can, this and this are the same thing. We can write them the same way. We can leave the 10 off if we want to because it's an implied understood log. So what we're going to do, we're going to use what we know about logs, and we're going to try to evaluate some logs here. So look at number 13. Logs equal what? What do logs always equal? Logs are what? Exponents. That's what I was trying to get. Logs are exponents. So I want to know what this equals. What would you need to put? How do you know? Because I'm thinking 7 to the what power would be 49. I need the power of 2 because logs equal exponents. How about number 14? Log base 3 of 27 would be what? Sorry, you're exactly right. Does everybody see where we're getting these numbers? 3 to the what power gives you 27? Sorry. How about 16? Yep. We'll do 15 while we're right here. What's that equal? So 10 to, it's 2. Why is it 2 and not 10? 10's the implied base. 10 to the second power gives me 100. How about 16? Look at y'all. Because anytime this number is 1, it's going to equal 0 for us. Because the only way to get 1 when you're raising to an exponent is if that exponent is 0. How about number 19? I'm going to skip down just a little bit. Y'all, I'm so proud. You don't? Let me slow down a little bit. Because 9 to the what power would give you 1 over 81. So because it's a fraction, I need the negative to flip it and then do the second. 20 is a little bit harder. By the way, for this, if you want to make a note, a lot of times if you're going from a whole number to a fraction or vice versa, then you want to look for a negative exponent because that's what's going to flip it over. So if you start with a fraction and you end with a whole number, or you start with a whole number and end with a fraction, you're probably looking for a negative exponent. If you start with a big number and you go down to a smaller number, can you think of what might be happening? What's the relationship with 64 and 4? What is it? 3. What about a 3? What happens there? 4 to the third is 64. But what do I have to raise 64 to in order to get 4? Negative is going to flip it. 1/3. Why is it 1/3? 1/3 is the same thing as what? If you have a 1/3 exponent, what is that the same as doing? Cubed root. That's exactly right. It's a third root. Remember that? Remember how that fraction, that denominator, that's that sunshine stuff we talked about. So if I go from a big number to a smaller number, I'm probably looking at a fraction exponent. Just some little helpful tips there to help you find those values. What do you think it is? Yeah. Log base 2 of 64. 6. Why is it 6? 2 to the what power gives you 64? 2, 4, 8, 16, 32, 64. Let's talk about change of base and I'll be done, I promise. So sometimes if you look on your calculator, we've talked a lot about base, right? But if you look on your calculator, it just says log. There's no base there. That's because your calculator operates in a base 10. Remember, that's that common base. If there's no base there, it's a base 10. So if you just push log, you're going to end up in base 10. So what we have to do is we do something called change of base. And what change of base does is it allows everything to be in base 10 so we can use our calculator to find the answer. So if I have log base b of a, I could evaluate that by doing the log of a divided by the log of b. And both of these, because there's no base there, is a little 10. But you can do this for any base as long as the base is the same on the top and the bottom. So let me show you what I'm talking about. And let's just take one we already did that we know the answer to. What was that one we just did? Log base 2 of 64. If I write that in change of base form, okay, it's going to be the log of 64 divided by the log of 2. So take out your calculator. Apologize for not having this ready to go. And let's do. All right, so we had log 64. So I'm going to do, because I'm dividing and this is an operation on the calculator, I'm going to do a parentheses. I'm going to do log 64 divided by log of 2. Just for example, the one we just did, log base 2 of 64, we know that the answer to that is 6, right? So I just want to show you how in your calculator, that's how you do change of base. Can everybody do that? Make sure you can input that on your calculator and get the right answer. That way you know how to do the rest of your homework here. So the reason this is convenient is because all logs are not perfect numbers, right? Sometimes we can't just evaluate in our head like we've been doing. Like number 21. 21 says the log of base 16 of 64. Well, that's kind of hard, right? I don't know what I can raise 16 to get 64. And I might could change the bases and get these both to be a base of 2, but we'll get into all that later. What I'm going to do is use my calculator, and I'm going to do this. Log 64 divided by log 16. Does that make sense on how we're doing change of base? It's a really, really easy concept. I would put it in parentheses so that it keeps the numerator and the denominator apart. It doesn't necessarily have to be on this one because of the order of operations. It doesn't have to be here, but you might start doing some other stuff. It's a good habit to be in, but you don't have to. All right. Do y'all need me to do any more? Or y'all okay? That one's pretty straightforward, I think. 26? Yeah. All right, so 26 is log base 6 of 1 over 36. And you could probably do this one without doing a change of base. What should I get here? Do you know off the top of your head? I should get -2. You're exactly right. But if I did change a base, I'd need to do log of 1 over 36 divided by log of 6. So if I go back to my calculator, the log of 1 over 36 divided by log 6. I'll have to look at yours because I can't remember.